Welcome to the second half of our course. In this half, we'll focus strictly on algorithms and complexity. So far in the course, we talked about several data structures that help us write better structured code. We'll begin this section by covering the basics about algorithms. We'll talk about what algorithms are, why we should study them, and how we can measure the performance and complexity of an algorithm so that we can compare and contrast different algorithms. Next, we'll talk about two classes of algorithms used in pathfinding. These types of algorithms are depth-first search and breadth-first search. In this video, we'll begin by describing what an algorithm is and why we should care to study about them. We will then talk about how to calculate the complexity and performance of an algorithm so that we can compare algorithms against each other. An algorithm is a set of steps taken in order to solve a specific problem. For example, an algorithm that recommends news articles that a reader is likely to enjoy reading might include the following steps. First, we find an article that the user has not yet read. We then ask ourselves, is this article recent enough that we would want to recommend it? Is this article within the average word count that this user normally reads? Is this article about a topic that the user reads often? Does the user tend to watch embedded videos within articles whenever he or she reads the article? And if so, does this article contain such embedded videos? Based on the answers to each of these questions in this algorithm, we could calculate some sort of score, which we would then use to determine whether the article would be a good recommendation or not. Now, looking at the steps in the algorithm we just looked at, you may or may not think that this algorithm is efficient in terms of calculating the final score for the recommendation that we're after. Whether or not the recommendation is accurate is not really important for the purposes of this conversation. What we want to know is how long it would take to calculate a score for a specific article. This way, if a different algorithm comes along, we can compare them in terms of their complexity. So when trying to determine how long an article takes to run, the algorithm, you may think that the answer depends on what kind of hardware we have running the algorithm. When describing complexity of algorithms, what we take into account is not the hardware used or the programming language that was used to implement the algorithm, or anything else that may vary for that matter. Instead, we look at how the algorithm responds to changes in the size of its input. For this, we use something called Big O notation. Big O notation gives us a way to express how an algorithm performs as its input grows larger and larger. For example, let's consider an algorithm that sorts a list of numbers in either ascending or descending order. The algorithm performs the following steps. First, we take the first number in the list and compare it to the number next to it. If the number on the left is greater to the number on the right, we swap both numbers. If the number on the left is less than or equal to the number to the right, we ignore it and go on to the next step. Now we compare the next item in the list to the one next to it. We repeat the steps until you reach the end of the list. Then we start over again until no swaps were required throughout the path, at which point the list is fully sorted. While this algorithm may take very little time to sort a list of 7 numbers, it will take significantly longer to sort a list of, let's say, 1 million items. Also, there are cases when the algorithm will take less steps to sort the list. For example, if the list is already sorted, or only a couple of items are out of order. Consider the case when the list is completely sorted, but in reverse order. In this case, the algorithm will take the longest possible time to complete. There are two ways to calculate the Big O value of a function. The first way is to use a formal mathematical definition of Big O notation. The second way is what is most commonly used and is much easier for the rest of us to understand. and requires the following slightly simpler steps. We keep the term with the highest order of growth, and in programming terms, we find the slowest operation in the function. We then remove any constants from this function. For example, looking at the sorting algorithm we described earlier, we can calculate the big O value of it for two types of input. The best case scenario, when the list is already sorted, and the worst case scenario, when the list is completely sorted but in reverse order. So every item in the list will need to be swapped. So suppose we have a list with 7 items in it. If the list is already sorted, then the algorithm would simply check that every number in the list is already sorted and calculate that the list is completely sorted already. A total of 7 checks will be performed. So we can say that the big O value of this algorithm in the best case would be O of n, meaning that n checks were made with the list having n items in it. In this case, it would be a big O value of n representing the list with 7 numbers. In this video, we learned how to use big O notation to calculate the limiting behavior of an algorithm. You are now able to look at an algorithm and calculate its complexity. This is especially useful when comparing similar algorithms in order to determine which one is most optimal. In the next video, we'll take a look at depth first and breadth first searching, which are two ways used to traverse a graph. Practical applications for wanting to do this includes finding a path through a maze.